Hello, I hope you can hear me well. And so my talk will be about the system boot and the Coreboot, which is the project, open source or free software project, which is doing the booting of the computer instead of the BIOS. So first, an outline. So I will introduce briefly our projects. Then we have a look how the PC looks like nowadays in the point of buses and so on. Then there is a little catch. We don't have any RAM at start, so I will show you how to deal with this. And of course, how to init the RAM of the computer. Then we have plenty of buses to go through and stuff. So this will be the last slides and tables and of course the boot. So first, who we are. Coreboot, free software project, coreboot.org. It's very roughly says that it's a replacement BIOS for 250 boards. It's quite fast. We can boot your system in 500 milliseconds or 1,500. It depends on what you actually use. Tomorrow I will speak more about it in the embedded dev room. The focus or the deployment of Coreboot is mostly the security stuff, embedded systems, and so on, because you never know what the proprietary BIOS is doing. So the Secret Service also likes to know what's going on with their BIOSes. So we are targeting the embedded systems and, of course, clusters, because this is how the project started in the year 99. There was a huge cluster of computers, and if you tried to boot them, they will complain that there is no keyboard. So a guy must go around 1,000 computers, plug the keyboard, press F1, go to another computer, and so on and so on. So this was, let's say, the first where the project has been started. Okay. So here is Mr. PC. I think you should know it quite well, but maybe we can repeat some details. I'm not sure if I have mouse so I can point. So this is the CPUs. Now we have a multiple of them. Each CPU has now each memory controller. Here is the DRAM. This is the DIMMs you can replace on your board. Here is the North Bridge and South Bridge. And in between there is some kind of bus, which is FSB or hypertransport bus. Or between North Bridge and South Bridge there is also some buses. It doesn't matter which right now. And of course the South Bridge, which is having all your peripheral devices like USB drives, serial port and such stuff. And of course there is a flash which has this program, either the BIOS or the Coreboot if you replace it already. What is quite interesting on this slide is that the red parts must be done by the Coreboot while the system is booting. So it's a lot of stuff to do, and we need to do it very quickly. So here is a little fairy tale about how to start a computer. So if you push the button, then at the beginning there is kind of power sequencing. So when the computer is starting, there are many voltage regulators. So you must wait until all voltages are at the right levels, and then the CPU gets started. And CPU will fetch the first instruction, which is this instruction, E9. And this is the dump of the flash chip. So if you take out the flash chip or the BIOS chip, let's say, out of the computer, so this is the last 16 bytes of it. And here is the first instruction. So if you decode this instruction, in fact, it's a jump to another address. And because I'm not expecting that you can read the machine code by looking at it, so then you can go to the Coreboot and, oh look, here is the bootblock.elf, and you can run object dump on it, and you can immediately see what's going on. So my presentation will be somehow intermixed with what is going on in the machine, and then where you can find it in the Coreboot code base, so you can follow the steps. Okay, so at the beginning of our fairy tale, the computer starts in something which is called a real mode. This mode is 30 years old. It's like the first IBM PCs is 1980 were started in this mode. So the CPU is still compatible 30 years still, because of this binary compatibility stuff and so on. So it really starts in this real mode, which is kind of derived from 8-bit computers. So we can address in one place only 64 bytes of RAM and totally 1 megabyte of RAM, which is not very nice, because the Coreboot is written in C, and we want to use GCC to compile the stuff, and GCC on x86 is mostly producing the 32-bit code. So what we need to do is that we need to switch to protected mode in order to be able to execute 32-bit code. How is it done is written here. It's basically only a few instructions. We need to load some descriptor table, then we toggle some bits, and that's it. So it was quite fast. Okay, so in fact we have kind of only very little assembly stuff in our project because most of it is written in C, so this is kind of early beginning, like in the Linux kernel. When it starts, there is also kind of glue assembly, so it sets up the environment, so it's kind of sane. But here is our first problem. So maybe we want to set up also the stack. And you know, when you start the computer, you have no memory. So we need first somehow to cope with the fact that we want to run the C, and we don't have any stack. Without the stack, you cannot use the local variables. You cannot use the read-write global variables, because you are executing code from ROM memory where you cannot write it there. So you cannot do the instructions like push, pop, return. You cannot do anything of this. So basically how we solve it, there are two possibilities. One is to use a special compiler, which is called ROMCC. This was written like that 10 years ago by Eric Biederman. It's a C compiler written in one C file. It's very ugly, very big, quite bloated, but it has a very special thing. It uses only CPU registers instead of the RAM. So the local variables in C codes are just stored in the registers. So of course it means you have only 128 bytes of available space, but you need to live with that. Okay, or the second possibility, which is used on the modern CPUs, is the cache SRAM. It's a neat trick. You can load the cache, which will become valid with the garbage data from memory, and you can use it, because if you don't evict any cache lines, then it is a RAM. So it's like write-back cache, which never reaches a RAM. So that's basically a trick how to do that. So let's see, we are now in C and happy. So first C code is executed in file which is called romstage.c. This file is kind of main function which gets started in the C environment. In this file there is an early initialization of the chipset, and I will show you what's done there. Basically, I think you already read that, so we need to have access to the serial line because we want to read some debug messages and so on. So we need to set up the serial line so it works and we can do print case to our screen. Of course, we need to do the stuff to reach the serial line, so we need to set up the LPC bus and the hypertransport bus and so on in the meanwhile. I am not expecting that you can see this because this hole is quite big, but it's an invitation to read the code yourself. Basically, here is the start, is the cache SRAM. You can see here we need the LPC bus, here we need the serial line, oh look, and here we can print something on screen. So we can have a look more until when I'm done with this lecture. Then Carl Daniel will speak about the flash ROM. This will be about how to flash the flash chips on the motherboards, and then you can come to our stand at AW building, and we can have a look there, and we can talk more, of course, about this. Okay, so RAM init. So in this environment, we still run without any RAM. So even if I put out all RAM from the board outside, it will still boot and show those messages because we are using cache as RAM. And we at the end, we just print no RAM, so we don't continue anywhere. In fact, it would be possible to implement some game and so on. It's 64 kilobytes is plenty of RAM. So you are invited to do so if you feel you can do it. So RAM init, how does it work? So first we need to get some data from the DIMM modules. To get this data, there is another bus which is called I2C. It is reachable from something which is called SM bus controller. This was the green lines around the big scheme. You need to program the chipset, or it means the North bridge or CPU if the memory controller is in the CPU. You need to send some JDEC commands to the RAM, and basically you are done. So it looks quite easy, but it is not so. In fact, it's a very complex task, especially for DDR, DDR2 or DDR3 RAMs. I use the slog count to just count only the code without any command lines. So for the AMD in DDR, it's like 2,000 lines, DDR2 4,000, DDR3 8,000 lines. So it's non-trivial problem, and for the DDR2 there is another problem which is called DQS timing. You need to find a strobe signal which will assure that the right data is read from the memory, and this timing is quite crucial. So and also it depends on the temperature. So at the beginning you just need to find the right place where it starts to work and the place where it doesn't work again, and then you take the half of it. So it's quite complex and complicated. Of course, it's also depending on the PCB layout and temperature and such stuff. So excuse me, no time in 50 minutes for this. So then the RAM stage is executed. So in RAM stage we copy the Coreboot to the second stage. We run from RAM. In this stage we have to train the PCI Express link and do all the resource enumeration on the PCI bus, like set up the I/O ports and such stuff, and of course prepare also some kind of tables which are required for the operating system, and of course the ACPI and power management and so on. So basically a lot of stuff still needs to be done after the RAM is running. Okay, here is some information about the tables. So it's mostly IRQ routing tables. That means that it's depending on the board layout. You need to know which device has which IRQ line, and plus of course the ACPI, which is very big specification, and it contains, as I have written here, everything. So it's very general. A lot of stuff is hidden there, and of course we support it in the Coreboot. And last thing is to load something. It can be operating system, it can be some game, it can be very old legacy ROM like ROM Basic, which I have brought here, so you can program something in very ancient language. We use CBIOS. This is a compatibility layer between Coreboot and operating system. You know this from the QEMU, because when QEMU loads, you can see it. So QEMU is the layer in between which is used to load the operating system, like a legacy BIOS, let's say. So that's it. Many thanks, and please visit us at our booth. I would be glad to see you there, and I can explain more stuff in detail. And tomorrow I will have some timing talk at the Embedded F Room, and now the next one is Karl Daniel, which will be speaking about how to flash the flash chips on the motherboard. So thank you again. That's it.
Thank you very much.
Oh, many thanks.
Perfect timing.
Okay.